most extreme manifestation of this problem will occur in the case when the when the for which the partial derivatives of the loss are very different with respect to different optimization variables. So for large networks, what happens is all parameters in the network need to be updated with the back propagation. So the number of parameters, they can easily be maybe in millions in the large scale application, and we need to simultaneously run all the examples forward and backward through the network in order to compute the back propagation updates. So it is impractical to simultaneously run all these examples through the network to compute the gradient with respect to the entire data set in just one shot. So what happens is, at the beginning of the learning process, the weights are incorrect in such a degree that even a small sample of points can be used to create an excellent estimate of the gradient's direction. Okay, so this observation provides the practical, basically the foundation for what is called as stochastic gradient descent method and further its variants. So since the loss function of most loss optimization problems, that is the neural networks, they can be expressed as a linear sum of the losses with respect to individual points, we can more efficiently undertake this entire process with the point specific updates of stochastic gradient descent. So this type of gradient descent is called stochastic because uh, we cycle through the points in some random order, not in one shot. So the long term effect of this repeated updates is basically the same as that of the gradient descent, but computationally it becomes better. So each local gradient can be computed efficiently this way, which makes the stochastic gradient descent faster, of course, at the expense of accuracy in the gradient computation. One interesting property of this stochastic gradient descent is that even though it might not perform as well as the training data compared to that of gradient descent, but it performs comparably well on the test data. That is what is required, right? When we saw the challenges, one of the challenge was overfitting. So stochastic gradient descent mitigates this challenge. In mini batch stochastic gradient, we use a batch of say m samples, that is a subset of the samples of training points for the update. So mini batch stochastic gradient descent, it provides the best trade-off between the stability, speed, and memory requirements. So when we use the mini batch gradient descent, the outputs of a layer basically are in terms of matrices instead of vectors, and forward propagation, it requires the multiplication of weight matrix with the activation matrix. The same is true for the backward propagation also, in which matrices of gradients are maintained. So therefore, the implementation of mini batch stochastic gradient descent increases the memory requirement. Okay. Uh, so this is a limiting factor on the size of the mini batch. The size of the mini batch is regulated by the amount of the memory available on whichever hardware that is using. The update rule, however, remains the same for both stochastic gradient descent as well as the mini batch gradient descent. So beyond a certain batch size, which is typically of the order of few hundred points, uh, we do not gain much in terms of accuracy of gradient computation. So commonly, the powers of 2 as the size of mini batch are used because this choice will often provide the best efficiency on most hardware architectures also. So common values are 32 or 64 or 128 or 256, depending on how many samples actually you have. So this is a small structured data set which is used to show the stochastic gradient descent. So this is having 178 samples. And it is a tabular data set with numeric values, numeric features, example, the acidity, the sugar, the chlorides, etc., etc. So these 178 samples, basically, they are small, suitable for lightweight models. So SGD is suitable here because of the small clean nature of the data set. It will provide well-behaved gradients. Well-behaved gradients will imply the loss surface is smooth, no non-differentiable points are there, and so it is easy for the optimizer like SGD to converge with careful tuning of the learning parameter. Then we have the SGD of with momentum. So as I told you, the marble example when I was dealing with the challenges in the optimization. So think of SGD like pushing a ball that rolls based on the slope. So if the slope keeps changing directions, in the say if it encounters a zigzag valley, the ball jerks around. So momentum, what momentum does it? It provides that ball with some kind of velocity so that it can push through small bumps and it can glide slowly towards the minima. The update rule here changes uh, uh, with slightly, the which is including this fraction beta uh, of the previous update, delta xt minus 1, and the current negative gradient is also used, negative gradient of the loss function, and eta remains your learning rate. So instead of only considering the current slope like the vanilla gradient, this is adding an inertia from the past movement. This is what is called as momentum. Okay, and this is how the trajectory of the SGD with momentum looks like. So this is the minimum, actual minimum final convergence point, and these show the update direction. Okay, the change. So see what is happening. Uh, Momentum is building up with every iteration, and it is avoiding the zigzag. So in the starting you had quite an oscillation, and then the oscillations die out because of the momentum. So SGD with momentum fixes the instability and inefficiency of the vanilla SGD by taking into account the past gradient information and therefore stabilizing the update direction, as you can see in this figure also. So with every epoch, there is a stability in the update direction. The biggest limitation here is it also can be slow in the flat region. It can get stuck in small minimum or the plateaus, and of course this is also sensitive to the learning rate. So SGD is basically preferred for problems where simplicity and minimal computations are, whereas the SGD with momentum will perform better in the complex landscapes where convergence, speed, and the stability matter. So you are training a model on the data set where some features are very frequent and others are rare. But the problem with SGD with momentum is that it applies the same learning rate to all parameters. So this means if the features are quite frequent, they get updated a lot because their gradients appear often. Whereas the rare features, they get updated less frequently but with a small learning rate. So what happens is the rare features learn very slowly or sometimes almost not at all because the learning rate is not adapted. So momentum also keeps accumulating past gradients. So if the feature has a consistently high gradient, it keeps pushing updates, potentially overshooting. So in that case, AdaGrad comes into picture. So AdaGrad adapts the learning rate individually for each parameter is the sum of squares of the past gradient. Okay, so you can see the update rule has now changed here as compared to the SGD with momentum. We have the update at t plus 1 with the help of the previous and uh, um, having the learning rate divided by this capital T, which is the sustain and on testing for individually. So parameters with frequent updates will get smaller update LGT values. This will prevent overshooting. And parameters with rare updates, they retain larger learning rate. Okay, so this makes AdaGrad useful for sparse data where some features are appearing very frequently and some features are appearing very rarely. For example, in the NLP or the recommendation system problems, where some features occur less frequently than the others. So so the advantages of the AdaGrad are, as I said, adaptive in nature, and it performs well on the sparse data set. Challenges include that uh, accumulation of squared gradients is a challenge, and each squared term is positive and hence accumulated sum keeps growing, which in the end make the learning rate very, very small, and thus it may often may not reach to the optimum. So in this case, what can be done is uh, there is something called as RMS prop. So before that, this is an example of the sample data in which AdaGrad performs better than other optimizers by adapting learning rates per parameter. So this is an example of from the NLP for the sentiment analysis task. This is the text for which the sentiment has been found. Now comes the RMS, which is again an adaptive learning rate optimization algorithm. Uh, and it is designed to overcome the diminishing learning rate problem which was happening in the AdaGrad. Okay, so in RMS prop, we see the update rule has now changed to this, that is making the learning rate modified to this term. So what is happening here is the moving average is being used here. So this is the moving average, which is basically exponentially decaying average of the squared gradients. Okay, this is how the RMS prop is adjusting the learning rate for each parameter individually. So goal here is to adapt the learning rate based on the recent history of gradients. So what happens here is the GT is the gradient of the function at iteration t and eta is the learning rate. And this E of GT square is the exponentially weighted moving average of the squared gradients. And beta takes the value between 0 and 1. Basically, it is taken to be 0.9, and epsilon is taken here for again preventing the denominator to go to 0. So this way, this allows smoother progress along gentle slopes. So if you take the recent gradients to be larger, that is E of G square become large, then the entire step size becomes smaller. Whereas if the recent gradients are small, that is E of GT square is small, then the entire step size becomes large. So this is how RMS prop is mitigating the disadvantage that ADA-GRAD had. So this avoids the vanishing learning rates. Okay, so this keeps the optimization going, and even after many iterations. So this way, the learning rate for each step is scaled by a factor of 1 upon root of GT. Okay, where your GT updates using the decay and not the accumulation, unlike the ADA-GRAD that we saw here. Okay, so this is the major difference here. So unlike the ADA-GRAD, which would keep increasing GT, RMS prop is stabilizing this learning rate, which allows the continued learning with smaller but non-vanishing updates. So this also may lead to inconsistent updates in the early stages of training, because you can see that this is relying on the exponentially weighted moving average. So in the early stage, this may be very, very small, or this may be very large at the very frequent times. So learning rate is still manual because the suggested value is not always appropriate for every task. So this slide gives the example in which the RMS prop works better, that is the time series sensor data. Here the data is sparse and noisy and has uneven gradients. So in these kind of settings, the RMS prop performs very well because it handles the noisy gradients very well because of the adaptive learning rate on a per weight basis. So this works well in the uneven or the sparse features. So this is a 3D plot of the function 0.1 x square plus y square. So as you can see, it's an elliptical bowl shaped surface, which is steeper in the y-axis as compared to the x-axis. So this kind of topology or this kind of curvature is exactly why the optimizers like Adam and the RMS prop behave differently in each direction. So what happens here is, so if you take the RMS prop settings, you assume the learning rate to be 0.1, the decay rate, that is the moving average factor, to be 0.9. That was beta here. Okay, so this we are taking to be 0.9, and a small constant to avoid the denominator to go to 0 is 10 to the power minus 8, and we start initially from the 0.11, and initial squared gradient accumulator we take it to be 0, 0. So as we progress further with the formula, we get V1 to be nu times V0 plus 1 minus nu times G1 square. Okay, so when we use the values, you get it to be 0.004 comma 0.4. Similarly, when update the theta1 value to be using the formula of the ADA-GRAD, you get theta naught minus eta time. This is the exponential moving average, and now we make use of the final update using the final update rule of the RMS prop, which is given by this. So this is giving us the update to be 0.6838 comma 0.6838 for the time step t is equal to 1. Likewise, when we perform the same for t is equal to 2, This is the exponential moving average, and this is the weight update. So you get it to be 0.4792 times 0.4990. So this way, iteratively, when we perform for n steps, we get these updates. Okay. So this is the example for RMS prop. Now, what happens in the ravine shaped loss surfaces, just like the one that I showed you here? The gradient changes direction rapidly. Okay, so the RMS prop, basically it ends up zigzagging, which is a slower convergence. Okay, so to mitigate this, we have ADAM, which combines the advantages of RMS prop and momentum. So here the intuition is taking into account two things. One is the momentum like behavior, and the other is the RMS prop like behavior. And then we have the bias correction, which ensures that these moments are accurate in the early training. So this is how the ADAM combines the benefits of momentum and RMS prop. So ADAM computes exponential weighted moving average, that is the gradient MT, first moment estimate, the squared gradient, that is VT, the second moment estimate. And these are the recursive formulas for the first moment and the second moment. But since your M naught and V naught is equal to 0 in the early values of MT and VT, are biased towards 0. So this bias gets smaller as T increases, but is problematic at the beginning of the training, and that is why this bias correction is applied. So if you want the detailed mathematical proof of it, you can find it out using the expected value formula, that is expected value of MT. Using those formulas, you can find out that this is the bias correction factor that you get, that is 1 minus B1. B1 is the correction factor that is that we get between the initial and the as the time goes from t is equal to 0 to the t is equal to t. This is the correction factor that needs to be applied to uh, prevent that bias going towards 0. So with this, we can see that Adam takes smooth curved steps by using the advantages of RMS prop-like behavior and momentum behavior. Okay. So this is sample data for Adam. Basically, Adam works good for mostly all the data sets, especially in the CNN architecture and all that. It is efficient on the complex and high dimensional input as well. So we take the same example as we took for the RMS prop with the first moment as 0.9 and the second moment to be 0.999, epsilon to be 10 to the power minus 8, and initial we start at the same 1, 1. So when we find the gradient, the first moment, second moment after the bias correction, we get the update to be 0.9 and 0.9. Similarly, for t is equal to 2, we get the update to be 0.8 and 0.8. So by iteratively applying this procedure, you get these updates. Now, when we compare this with the RMS prop, so you can see that RMS prop is basically having high initial jumps. Okay, that is, so it is basically giving, initially it is jumping higher, and the updates in the y direction are different from that of the x direction, whereas Adam you can see that it takes more smooth and consistent updates. And from the graph also you can see that unlike the RMS prop, the Adam is consistent in both X and Y direction. This is because RMS prop is without the momentum is zigzagging. So RMS prop is making larger initial jumps, but then begins slowing down due to large VT, especially in the steep Y direction. And Adam keeps moving more consistently and smoothly because of the momentum term. As is visible here. Here, the RMS
I'm
prop
not
is
audible.
also. Am I not audible?
No, no, now it's audible.
Okay. Uh, was I not audible for the previous minutes?
Yes, ma'am.
How many minutes?
Just 2, 3 minutes.
Okay. Okay. I hope it is fine now. Is it fine now?
Yes, ma'am. Now it's fine.
Okay, so this since this is a simple function, here the more complex capturing optimizers are like the Adam is also overshooting, whereas the RMS prop is consistent and the SGD is also consistent. Okay, this is a very nice function, as you can see from the contour plots also. So in comparison, the SGD works well for the large, well-structured data set with consistent patterns, having balanced and dense features. So it is commonly used in image classification with CNNs, object detection. AdaGrad is best suited for NLP tasks, having sparse data and infrequent features, and it is commonly used in the text and the recommenders domain. RMS prop is basically suited for non-stationary and time-dependent data sets which are having noisy or sequential data, and the patterns evolve over time. So these are very popular in the time series or the speech or the RNNs. Adam is generally accepted for the fast convergence where the data sets are large scale data sets and you have deep neural networks, noisy gradients. So Adam is commonly used in the transformers or the NLP tasks having BERT or GPT or image segmentation task, fine tuning, etc. So now we move on to the second order method. So as we had already seen that the loss surfaces in the form of cliffs and valleys, they are not desirable because they come with a certain level of instability. So if we are having a small change in some of the weights, it can either change the loss in a tiny way or suddenly change the loss by very large amount. That can that the solution is goes far away from the true optimum. So, one way of understanding this behavior is that sharing parameters across the layers it naturally leads to the higher order effects of weight perturbations on the loss surface. Okay, so this is because the shared weights of different layers are multiplied during the neural network prediction, and a first order gradient is becomes insufficient to the model to model the effect of the curvature in the loss function. So basically, then come the second order methods, which can give us more information about the curvature of the loss surface, that is measuring the change in the gradient along a particular direction well. Okay, so such settings are often addressed in the techniques that either clip the gradient or they explicitly use the curvature information, that is the second order derivative of the loss function. So here is one such method called the Newton method, which makes use of the second order derivatives of the loss surface in terms of Hessian matrix, because we will be dealing with the multivariable function. So to capture the second order derivatives, we have to go for the Hessian. So consider the parameter vector W, W bar, having some d parameters, which is expressed in the columns. This is a transpose, and the second order derivative of the loss function is given by the Hij, where your H is d by d dimension Hessian matrix. Okay. Um, the ijth entry is the Hij, which is given by the second order derivative of the loss function. Uh, although this is not, I mean, all those optimizers that we have seen, this Hessian was not used in there. Although we definitely have more advantage of these kinds of method, but we will also see the disadvantage as to why this was not used in the previous optimizers. So we can write the quadratic approximation of the loss function in the Taylor series expansion, given by f of w naught plus w minus w naught f dash of w naught plus w minus w naught the whole square by 2 f double dash. This is the single variable case, and the multivariable case is expressed in terms of the matrices of the weight matrices, the weights and the Jacobian. So Hessian is computed at w naught bar. So here the parameter vectors w bar and the w naught bar are d-dimensional. Okay, this is a quadratic approximation, and you can simplify simply set the gradient to be 0, so which gives us this equation, that is gradient of the loss function j of w bar to be 0. So this reduces the Taylor approximation, the gradient of Taylor approximation to be gradient of j of w naught bar plus h of w bar minus w naught equal to 0. So this is the gradient of Taylor approximation. So we can rearrange these optimality conditions to obtain this Newton update. That is, the weights are updated using W naught bar minus H inverse gradient of J of W naught bar. Okay. So here your update is involving the inverse of the Hessian matrix and the gradient of the loss function. Okay. So this update is directly obtained from the optimality condition, and therefore there is no learning rate here. So this update is approximating your loss function with a quadratic function and moving exactly to the say, so let me show you the figure here. Okay, I think the figure that you, if you remember the figure of the valley, so this update is basically approximating the loss function with a quadratic function. So that is where the biggest advantage of this method is. And in a single step, it is moving exactly to the minimum point. Okay. So in the first order methods, when we saw the loss surface geometry, we saw that in the high curvature loss surfaces, the first order method, they bounced back and forth along the directions of the high curvature. So here the main difference from the update rule of steepest descent is that the update is carried out directly with the help of inverse of Hessian and the steepest direction. So this multiplication is what is changing the direction of the steepest gradient descent. So that you can take larger steps. So in that direction, for the better improvement of the objective function. So the multiplication with the inverse Hessian is the main important part of this entire procedure in changing the direction of the steepest gradient descent, so that we can take larger steps in that direction in which the loss function is minimizing, even if the instantaneous rate of change in that direction is not as large as the steepest descent direction because of the multiplication of the Hessian. So Hessian basically it encodes how fast the gradient is changing in each direction. So changing gradients are bad for larger update because we might uh, we might worsen the objective function. So if the signs of many components of the gradient change during the step, so it is always profitable to move in the directions where the ratio of the gradient to the rate of change of gradient is large, so that we can take larger steps without causing harm to the optimization. So pre-multiplication with the inverse of the Hessian achieves this goal. So this is how the effect of multiplication, pre-multiplication of the steepest descent direction with the inverse Hessian uh, look like. Okay, so it is helpful to it is helpful to reconcile, I mean in the sense that the steepest direction has changed, and it also ensures that the direction is pointing in the optimum point, towards the optimum point. So this is what the role of inverse Hessian is, the multiplication of the gradient by the inverse Hessian. Instead of following the steepest descent direction, it allows larger and more effective steps even in directions where the gradient magnitude is not the highest. So Hessian matrix, it basically encodes the rate at which the gradient itself changes, that is the curvature. And the directions where the gradient changes slowly are more stable for larger updates. So pre-multiplying the gradient with the inverse Hessian identifies and emphasizes these stable directions, allowing the optimizer to move confidently and effectively through the parameter space. So this is a small numerical example for demonstrating the Newton's method. So this is a nice looking convex quadratic function, and we start with 1 1, the initial value 1 1, and apply the Newton method, that is by calculating the gradient. You find the Hessian gradient of the Jacobian, you find the Hessian, and apply the Newton's update rule by updating this point with the difference of this point with the the multiplication of the inverse of Hessian with the gradient of the loss function. So in a single step, we reach the optimum point. So this works because the second order Taylor approximation is exact for a quadratic function, and Newton's method solves it in only one iteration. But in reality, we don't have, the neural networks do not have the exact quadratic, so we have to use the quadratic approximation. So the most large scale neural network, the Hessian is too large to store or compute explicitly. So it is very uncommon to have neural networks with millions of parameters. Trying to compute the inverse of such a big Hessian matrix is very, very computationally expensive. So therefore, many approximations and variations to this method have been developed. And examples are the Hessian free optimization or conjugate gradient method or quasi-Newton methods that approximate the Hessian, where the basic goal is to make the second order updates without exactly computing the Hessian. So these are basically used when the second order information is also desired and the loss surface topography is highly curvaturely treacherous. So this is another example on the non-quadratic function with the help of the Newton's method. So again, we use the gradient, the initial weights to be 0, 0. We find out the value of the function at this initial point, and start with the update rule by computing the Hessian matrix at this point, which is 2.91 and 8.91. Then we compute the Hessian matrix, and then we take the inverse, and when we do the Newton's update, we get the value to be minus 1.1745. And so you see in this example, the update is also the initial value was minus 1, and after one step the update has is this much. So this is in the non-convex setup, we can make use of this Newton's method by considering an approximation of this non-convex function to a quadratic function. Or you can also go for Hessian free optimization. So with this, I end this talk. Any doubts here? Was my voice audible?